Hi, you guys. Today I have with me problem 2.47 and I think 2.45 in another textbook, but the 14th and 15th edition of Young and Freedman's University Physics textbook. So let's get started on this problem. But before I go ahead and do that, please don't forget to like and share and subscribe to my channel if it's helpful. Thank you. I mean, if you find the videos I make helpful. Okay, thank you. So a 15-kilogram rock is dropped from rest on the Earth and reaches the ground in 1.75 seconds. When it is dropped from the same height on Saturn's satellite, I'm not even going to attempt to pronounce that. Enceladus? Okay. Give me a second. I'm going to search up how to say it. Okay, according to Google, it's Enceladus, like this.
Enceladus.
Okay, Enceladus. The rock reaches the ground in 18.6 seconds. What is the acceleration due to gravity on Enceladus? Okay, so let's go ahead and just figure out and draw out the problem for ourselves. So a 15-kilogram rock is dropped from rest on Earth. Okay, so let's label that. Let's do blue for Earth because blue for water. So this is going to be Earth. And we have some sort of ground, and we're going to have some rock. Let's say this rock is going to be in the color black, and it's going to be dropped. Starts from rest, right? So VI is equal to 0 meters per second, and this journey takes 1.75 seconds. Okay, so that's our diagram. And when it's dropped from the same height on Saturn's satellite Enceladus, so now let's do Saturn. And I don't really know, I know Saturn has like rings, right? But, and I'm gonna use brown. Okay, so Saturn. But Saturn gives me orange vibes, so let's make the rock orange. Okay. And we have a rock, again, it's identical. Same rock. When it's dropped, oh, wait, okay, let's pretend Enceladus is brown and orange, but same thing. Okay, the colors don't matter. Okay, Enceladus, the rock is dropped from Enceladus and it reaches the ground. So again, from rest, VI is equal to 0 meters per second, and it reaches the ground in 18.6 seconds. And let me just label that that's the time. 0.6 seconds. So what is the acceleration due to gravity on Enceladus? Okay, well, one thing we should probably note is that on Earth, acceleration due to gravity is equal to 9.8 meters per second squared. So what is the acceleration on Enceladus? That's what we want to figure out. Okay, so now that we have a diagram, let's just go ahead and write down all of our knowns and unknowns. Okay, so do that in green. So knowns. So we know that, again, on Earth, VI is equal to 0 meters per second. The distance it travels, okay, so important, we didn't do this in our diagram, but we want to define what's positive and what's negative, and like what direction is positive and what direction is negative. So let's do that here. I don't want to use blue for that. I'm gonna use, let's do green. Okay. So up is positive and down is negative. Awesome. Okay, so now down, since a rock is being dropped, that means it's traveling downwards, which means that we're going to have like minus h, right? Or I guess it's implied in the question, like when we solve for this, it's going to turn out to be minus h. So we can just write like it travels like a distance h. Okay. or a displacement h. Okay. So then we know that the time that it takes is 1.75 seconds. And acceleration due to gravity, because acceleration is downwards, acceleration is going to be, so I'm going to do gravity on Earth, so GE, that's going to be minus 9.8 meters per second squared, right? And we're going to automatically end up with a minus h because of the nature of the question, right? But yeah, those are our knowns for Earth. And just note that technically h isn't a known. We don't know what it is. So actually, I'm going to go ahead and just write down that we don't know what exactly this distance is because it doesn't really say in the question. But what we do know, what we do have is some knowns for Enceladus. That's such a fun name. Okay, so Enceladus. I really like my writing today. I don't want to jinx it. Okay, so Enceladus has, again, a VI of 0 meters per second. It travels the same distance on Earth and on Enceladus. So these are equal. Okay, but we don't know what this is either, actually. The time it takes is 18.6 seconds. And we don't know what the, oh, I don't want to write GE, so because Enceladus also starts with an E and Earth also starts with an E, so I'm just going to write GSE, right? So Saturn, Enceladus. Okay. All right, we don't know what this is, but we are looking for the acceleration due to gravity on Enceladus. So this is actually what we're looking for. So we want to use, remember how we solve a one-dimensional problem, one-dimensional kinematics problem, and we use one of the 5 kinematic equations. And so if we look here, we have the I, we don't have D, we have T, we don't have GSE. So we have 2 knowns and 2 unknowns, but for the 5 kinematic equations, we need 3 knowns and 1 unknown. So we can't use this. So if we want to find out this, we need this first. And to figure out, sorry, that's kind of messy and I'm kind of on this street today where everything actually looks really nice. So let's just make this like yellow. Okay, so we need to figure out, oh, that was horrible. There we go. Yeah, so we need to figure out what D is. And to do that, we have to solve for, we need to solve for this D, right? Because if we solve for this D, then we can use that to get this, and then we'll have 3 knowns and then 2 unknown. Or sorry, 1 unknown. I don't know why I can't count. Okay, 1 unknown. That's what we want. So we need to solve for D on Earth. And this is perfect, right? Perfect. Because we have 3 knowns and 1 unknown, right? So we have VI, we have T, and we have GE, and then we need D. So we can use one of our 5 kinematic equations, right? So let's do our solving right over on our right side. So let's use green to solve, okay? So Earth, I'm just going to write down what we're doing. So solve for D, that's step 1. And then 2, use D for Enceladus. Just get GSE. And this is what we want. Okay, cool. So let's do that. So which one of our 5 kinematic equations has VI, T, GE, and D? it's going to be this equation right over here. It's going to be d is equal to VIT plus half of AT squared. And that is going to be, let's plug in our values, right? So d is what we don't know what d is, right? So this is what we're trying to figure out, but it's going to be, but if we plug in all of our values for VIT half, VIT and A, then we'll get d. So VI is 0, right? Then we have minus, okay, half, and what's going to be our acceleration? Oh, sorry, plus. Sorry, plus. Oh, sorry, no. Yeah, plus. Okay, plus A is going to be minus 9.8, and then T is, what did we say? 1.75 squared. Okay, so I'm going to plug that in with my calculator just to double check my work. .5 times minus 9.8 times 1.75 squared. And I am getting minus 15.00. I'm going to double check because that's actually not the value that I got. Oh, actually, no, it is. It is. I was looking at a different problem. Yeah. So 15.00625 meters. And this makes sense that we're going, in the negative direction because it's falling down. And that's what we predicted at the beginning, right? So that makes sense. That's our D value. So D is, I'm just going to write that down right over here. Green. D is equal to minus 15.00625 minus 15.00625. Now, great, we have one known, 2 known, and 3 known. And now we can just solve for GSE. So we solve for D, and now we can do part 2, right? So this was part 1, and I'm just going to go ahead and erase this. And now let's do part 2. So part 2, we just want GSE. And how are we going to do that? Well, what knowns do we have? We have VI, we have VI now, we have D, and we have T. And we want to find out what GSE is, or like what A is, right? So again, we're just going to use the same equation, but this time we're going to be isolating for A instead of solving for D. So let's write that down. So we have D is equal to VIT plus half of AT squared. And we want to solve for A. So let's isolate for A. D minus VIT D minus VIT is equal to half of AT squared. Then we can do 2 times D minus VIT is equal to AT squared, and divide both sides by T squared. And if we want to solve for A, we just have to do 2D minus VIT over T squared. Okay, so in my notes, I didn't do it this way, so I'm just going to quickly I don't like how I wrote that down. I'm going to double check my work just to make sure that I didn't make any mistakes. So let me do that. Okay, you know what? Let's go through and just plug in our values. And if I don't get the same one, then I'll check where I went wrong. But this should be right. Okay, so let's plug in our values. So 2 times D, which is minus 15.00625, minus VI, which is 0, so minus 0. And then t squared is 18.6 squared. And so when I solve that, I'm just gonna go ahead and write down our final answer right over here. So times 2 divided by 18.6 squared. Yep, and I'm getting acceleration is minus 0.08675 meters per second squared. And that's the answer that I got, and I checked that answer earlier on as well. So that's the correct answer. So the gravity is 0.08675 meters per second squared. That's the magnitude. And then you just put a plus or minus depending on which direction you set as your positive and negative. So yeah, GSE is equal to minus 0.0868 meters per second squared. Awesome. And that's our solution. I hope that was helpful. And if you have any questions, comments, concerns, please don't hesitate to leave those in the comments or send me an email. And please don't forget to like and subscribe, and see you next time. Bye.